I got something with me right here. This one is a car, a little Lego car. And as we can see, the car is broken, obviously. And what we are going to do today is we are actually solving a hands-on showcase or a hands-on digital forensic investigation case, which we have done within our research institution. And this is all by helping different people. So especially in this case, we are helping some of the insurance company people. And I have a little representative here too from an insurance company. This is this little guy. He's called Pete. You may or may not know him already from my previous talk or previous video recording on my paper I presented at SECURWARE. But when we want to solve a digital forensics case, we first need some fundamentals, right? So let's begin with getting some automotive security or automotive fundamentals overall. So in general, automotive systems introduce a lot of different core components. It differs between the different manufacturers and the different types, obviously, but also on how well equipped your car is. But in general, we can separate modern vehicles into different, or we can declare different core components of modern vehicles. One core component here is, for example, the telematics control unit. This control unit is responsible for communicating, for example, with the backend of the vehicle manufacturer. But also interesting here is the comfort system. This is something that suits the passengers. So everything related to the temperature within the cars, to everything that you can move the seats, for example, this is all comfort systems. Another interesting component or core component we have in modern vehicles is the eCall system. The system automatically detects if an accident is happening, and then it sends a so-called eCall to, for example, the police or any other entities to send help to the vehicle. Next one, kind of related to eCall, is the airbag. Airbag, we all know, is something that explodes if we have a crash and saves the participants from serious injuries. Next up is the gateway, because in modern vehicles, we have a lot of different bus types, so different communication protocols and different components that speak different protocols, so different languages, let's say. And the gateway is kind of a translator for those components. So it gets information from another component that communicates, for example, using the CAN bus, to another component that's, for example, only able to speak the LIN bus. So the gateway is kind of a middleman between those components. Next up, battery-related systems. This is really interesting if we deal with electrical vehicles, because there are a lot of battery-related systems. Its aims is basically to monitor the battery, monitor the power usage to get the most out of the battery. Next up would be endpoint devices. Endpoint devices are components that are brought by the customer or the participants of the vehicle. So let's say smartphones, OBD dongles that can be plugged into the OBD dongle right under the steering wheel. Those are also connecting with the vehicle, but share a lot of information from the passengers, for example. Next up is the infotainment system. This is the most present system we have in modern vehicles. It's everything related on, for example, if we have a Tesla on the right-hand side, the big monitor, or other vehicles where we have, for example, an integrated navigation system, music, radio, everything related to this is part of the infotainment system. Next up would be the ignition system, and kind of related to this is the immobilizer. The ignition system is responsible for starting the engine itself. So enabling or starting the motor or starting the battery if you have an electrical vehicle. The immobilizer system is responsible to determine if, for example, the key, which is brought by the user of the vehicle, is the correct key. So the vehicle is actually allowed to start or even allowed to open the doors. Next up would be a navigation system. Sometimes it is separated from the infotainment system and sometimes not, but it is pretty relevant or interesting in modern vehicles because it stores a lot of information related to the route and also route-related information such as speed and which paths are taken by the vehicle. And last but not least, another core component of modern vehicles are safety monitoring systems. So this is everything related to safety stuff or safety information within the vehicle. So this could be, for example, something like automatic braking or adjusting the speed in a safe manner so the vehicle is adjusting the speed by itself, basically. But modern vehicles are not only introducing in-vehicle components. Modern vehicles are also highly interconnected with the vehicle ecosystem. A few examples can we see here on the slide. So one would be, for example, Car2X. Car2X, for example, is communication between the car and X, so something other, like the back end, like other vehicles, for example. And this is pretty interesting too, because there we have a lot of interconnection between the car and other entities. Another core component which interconnects with or interchanges information with modern vehicles are smartphones. So we can connect, for example, our mobile phone or our smartphone with the infotainment system via Bluetooth, for example, and exchange information, stream our favorite playlist, but also use the in-vehicle systems as to call our buddies. Also interesting in case of communication between the vehicle and other entities are smart homes, so smart home integration. Modern vehicles can introduce services such as automatic opening of, for example, the garage, or if the vehicle is communicating with the smart home, for example, via the telematics control unit, it detects if the vehicle is nearby and, for example, heats up the living room for user. Next up would be backend services. I already mentioned them before. This is all communication between the vehicle and a backend, for example, from the manufacturer. Interesting here is also that the backend is not only offered by the manufacturer, also backends from any third parties. Interesting. Let's say if we are able to stream our favorite Spotify playlist in modern vehicles, our vehicle is communicating with the backend from Spotify, actually. Next up would be traffic lights, also related to Car2X, to detect if there is, for example, a vehicle coming through and no other vehicles on a crossroad, for example, then it switches to green automatically. And last but not least, very interesting too, are OBD dongles. Those are little small dongles, which I already introduced before. This can be plugged into the OBD interface right under the steering wheel for most vehicles. And this streams some relevant information such as speed or errors from the engine to another device, something like the smartphone. We already saw in those few slides that we have a lot of in-vehicle systems, but also a lot of interconnections between our modern vehicles we can see right now on the streets, and also all the vehicles which we can see here on the slide. So what we pretty easily can identify right now, modern vehicles are pretty complex, right? So we have a lot of in-vehicle systems, but we also have a lot of software right now due to all those new services and technologies. So right now we know a lot of stuff about, or some fundamentals at least, about automotive systems. But to actually solve a case in the context or the domain of automotive digital forensics, we also need some digital forensic fundamentals, right? So the general goal of digital forensics is basically reconstruction of events. In the past, something happens, including some digital devices, smartphones, laptops, servers, or even cars. And then something happens afterwards, and then we need to reconstruct what happened actually. This is the goal of digital forensic investigations, pretty simply explained. And to reconstruct this, we usually have some predefined processes. There are a lot of different processes. It's always depending on the domain we are in, but in general, we have 5 different steps. First one would be forensic readiness. So this is where we have to identify if we actually have digital evidence which we are able to consume, or do you have the capability to collect this evidence? Just imagine if you are a forensic investigator and you need, for example, to perform a forensic investigation on a satellite. Obviously, it's pretty hard to get information directly via plug and play from the satellite because it's in outer space. So this is all related to forensic readiness. Second step would be extraction. So after we have identified that we are actually able to consume or collect information, we need to actually extract it from the digital or from the evidence items we are interested in. So this is everything related to, for example, tools that collects information from hard drives, but also embedded forensics. This means that we're actually connecting, for example, through debugging interfaces such as JTAG or something else to the device and collect the information in a physical manner. Step 3 is analysis. So after we have collected a lot of this information, we then can analyze it. So therefore we need data interpretation. Let's say we have something like a binary stream or stream of binary data. We actually need to analyze it for us to later interpret it in step 4. So as I said, step 4 is interpretation. So after we have collected a lot of evidence, we've analyzed all this evidence, we then need to interpret it. So this is actually the reconstruction of the events I just mentioned before. So here we have different parts which happened at different timestamps, for example, and then we are interpreting at timestamp 1, this happens, at timestamp 2, this happens. And this is one of the main tasks here. Last but not least, maybe one of the most important points or most important steps in the process is reporting. Here we need to document everything we did throughout the investigation, and then we need to document it in a reasonably way. Reporting is pretty key because in digital forensic investigations, we sometimes have to present our results in front of court. So if we present it in front of court, we need to present it in an understandable way. So not that technical, but also a detailed representation on what actually occurred, how we got to the reconstruction of the events. This is an interesting quote, which is directly linked to digital forensics from Dr. Edmund Locard. It's called the Locard's principle in digital forensics. It's pretty convenient for us as forensic investigators, not even digital forensics, also general forensics. It states that any action someone is performing actually leaves a trace. And this trace is not always that easy to collect. So let's say if we have a digital forensic investigation, we can definitely state that any action in a digital manner or a digital world leaves actually a trace. Even if for example, an attacker deletes all the logs, it actually leaves a trace. Because if we look on the physical area, we have memory wear due to, for example, this interconnection between different systems. But this, for example, is extremely hard to identify. I don't even know if it's sometimes not even able to identify. But in a physical manner, for example, in this case, it's actually leaving a trace. So this is pretty convenient because now we can identify relevant questions we want to answer in digital forensic investigations. In general, we can answer, or we aim to answer, the so-called 6 W's in forensic investigations. It's the why, who, what, when, how, and where. Usually we aim to answer all those questions, but sometimes we are not able to answer all those questions, sometimes even due to privacy concerns. But in general, we usually focus on those three words and the corresponding questions. As I already stated, there are some different domains or different, challenges, or not even challenges, different areas where we can perform digital forensics. Depending on the domain we are in or the discipline we are looking at, there are some minor changes, for example, in the process or in specific steps of the process, such as extraction, analysis, interpretation, privacy, and so on. So here's a minor list of some examples, like mobile forensics, looking at smartphones, network forensics, looking at the network consuming logs, cloud forensics, looking at everything that is related to the cloud, computer forensics or IoT forensics, or related to computers or IoT devices. And last but not least, automotive forensics, which we look at today. So let's build up some fundamentals on automotive digital forensics, right? So we have some fundamentals of automotive systems right now, but also on digital forensics. So next step, before we actually are able to jump into the case, is let's build up some fundamentals on automotive digital forensics. What is this even about automotive digital forensics? Well, it's pretty easy because automotive digital forensics is the implementation of technologies, processes, and methodologies which we already know from the digital forensic science. So everything we already know by now because we have the fundamentals, right? But it's not only the implementation of stuff we already know, it's also introducing new relevant stuff which we don't know yet, but it should or could depend on methodologies, for example, or processes we already know from the digital forensic science, because it has proven that it's working right now. And we already saw in the digital forensic, the automotive fundamentals, that vehicles are not only limited to everything that is installed in a modern vehicle, so not all components. It's also about the interconnection between different components or entities that communicate with our modern vehicles. So in automotive digital forensic investigations, we are not only looking at stuff built in within the vehicle or built into the vehicle, we are also looking at stuff from the vehicle ecosystem. So everything connected to our modern vehicle systems. The process is pretty similar to this, or the process in automotive digital forensic investigations is pretty similar to the process we already have seen from digital forensic science. We also have a forensic readiness phase where we need to identify data sources and potential data exchange methods to collect the information. Afterwards, we can perform data acquisition. This is where we actually determine the variant we are dealing with, so the actual vehicle we have in front of us. Then we determine what data sources we want to collect and what the interfaces and data exchange methods we want to use. Afterwards, we can look if there's existing tools to collect this information. If not, we need to organize tools that are able to consume this information, or we even have to program them ourselves. And afterwards is the actual acquisition itself, including the duplication of the original evidence. This allows us, or this enables us to not tamper with the actual evidence. So if someone wants to reproduce our results afterwards, for example, in front of court, there's not an issue if we've, for example, tampered or changed information on the digital evidence and the original digital evidence. Phase C is data analysis. This is where we actually look into the data. We look for relevant data sections or events we want to focus on. And then we create timelines and so-called evidence trails. This is the reconstruction of what happened, actually. Last but not least, I mentioned it before, documentation, documentation, documentation. So this is where we have to collect all the documentation from the prior phases and create a final report, which we also need to review multiple times. So now we have the process. And we already can see here in the forensic readiness phase, we actually need to look at where is relevant information stored, right? So at the beginning, I showed some components in the automotive fundamentals, so battery-rated systems, endpoint devices, telematics control unit, and so on. And it's basically pretty straightforward to define data classes. Those are firmware, communication data, user data, safety data, and security data, and map them where are they or located at, or where do we suspect this data to be located at. So for one example, a comfort system. Comfort system obviously holds firmware because somehow it needs to operate. Next up is communication data because it needs to actually communicate with, for example, the infotainment system, but also other comfort system related components such as temperature regulation. And it obviously holds user data because if we, for example, enable our seat to be perfectly fine with how big we are and it suits us perfectly, this is actually data that can be translated or interpreted to be for a specific user. But automotive digital forensics, similar to general digital forensics, states or implements or introduces even a lot of challenges we have to deal with. In general, it's all about correlation of data, integrity of data, interpretation of data, collection of data, but also privacy and security challenges in those areas. For example, we've seen that modern vehicles are pretty complex, so they introduce also a lot of proprietary tools that are, for example, developed by the manufacturer. And in this case, it's pretty hard to address challenges in correlation and also interpretation, because usually we don't have internal documentation of the manufacturers on the one side, but also we don't have tools or manufacturer-specific tools. So we need to program them, for example, ourselves or ask the manufacturer. So to address all those challenges, we need to look at current research. And current research addresses, for example, integrity by introducing technologies we already know from common IT into the automotive domain. So now we have built a pretty good and solid foundation on automotive systems, on digital forensics, and on automotive digital forensics. So I would say let's just straight jump into the result, or not the result, even in the case, because we obviously want to solve the case together. So I already showed you before the small vehicle. And the small vehicle is also red, and it represents, for example, a Tesla, because it's pretty hard for me to get a Tesla into my room, obviously, that is broken. So in the case, we have our investigator or insurance forensic investigator, Pete, which gets a call from the police. And the police officer says that there happened an accident and they need his expertise to perform a forensic investigation on the vehicle. So he jumps into the car, drives to the scene, and talks with the police officer. The police officer tells us some information. So they have a Tesla vehicle, a Model 3, which we can see here in a screenshot. And the Tesla model or the vehicle was automatically parking into a parking lot. And then suddenly, so this is what the driver told the police officer, the vehicle started somehow automatically and drove down a hill and broke. So far, so good. So all this information is pretty interesting for Pete as a forensic investigator. But at the scene, there's something wrong. He is not able to spot the vehicle. It already got removed from the scene. So he talks back to the forensic investigator or the police officer and asks him, where is the vehicle? If there is no evidence item, how is he even able to perform a forensic investigation? So this is where Pete got an airbag ECU. This is the ECU responsible for communication with the deployment entities within the car, but it also logs some relevant information right before the actual crash. So sadly, Pete only got the airbag ECU, which we can see here on the screen. So the main question Pete asks to itself is, what could he or actually we obviously, or what we can actually do with this evidence item? Well, we can, on the one hand, try to analyze the ECU somehow. So look if there is available tools which we can use to collect the information. Look for embedded forensic techniques which we could apply to the ECU. But we also could install it into another Tesla and collect the information. However, there is not the option for Pete to install it into another Tesla because of two main reasons. First one, there is not a Tesla available for Pete to use this for. And also, he doesn't know if he's installing it into another ECU, if it's even working, but also if it's even changing some information on the ECU. So in the worst case scenario here, if it's installing it into another Tesla, it's overriding all the information within the ECU, so nothing to analyze. So in order to check what we're actually dealing with, we first need to dismantle it, because here on the picture, we can see that we have on the bottom two small interfaces, but also this black plastic stuff around the device. So let's jump straight into the component. And there is something that Pete spots right away. Here in the screenshot, we can see that the ECU is damaged, or looks at least damaged. So this is not how such a board, such a PLC should actually look like, right? So we have some weird interferences on the hardware. So this is not very good. So the main question that states here, what could we actually do, right? So again, we have different options. We can just try to consume information or collect information with existing tools. But we could also maybe try to clean it, to repair it, but it's pretty hard here, or pretty dangerous here, to interfere with the information stored on the component if we try to interact with it in a embedded forensic way. So we are happy that there is an own EDR tool, so an event data recorder tool from Tesla itself. This tool allows us to basically power on the ECU, the ABAC ECU, and collect this information from it using the tool. However, this tool is not working. So there are different options why this is not working. Either it's not supporting the component we have to deal with, we did something wrong with the setup, or the device is actually damaged, so we are not able to collect the information through the standard way using the ADR tool. So since we documented everything, we are following the process right now with Pete together. We are not using it wrong. If we check back to what the tool is supporting, we already see that it also supports the common ABAC ECUs from modern Tesla vehicles, modern Tesla Model 3s. So there's something wrong. So the data is located anywhere on the chip, and usually it's a flash storage technology used. What we could do is we could desolder the storage device and try to analyze in another way. What we could do is we could desolder it and read it with an external adapter. Usually those external adapters are known from mobile forensics. If you, for example, exclude flash chips from smartphones, there are a lot of external adapters we could use. However, as I already stated before, data interpretation is a challenge we're facing in automotive digital forensics. Again, here, if we extract the information in a raw data format, we just have a hexadecimal blob or a binary blob. But we are not able to interpret this information because the interpretation itself is intellectual property from Tesla. Well, so the only option here is desoldering the storage device and building it into another ABAC ECU. Because we still need to somehow rely on interpretation, and interpretation only comes from Tesla, so from Tesla's EDR tool. But this is pretty interesting here because this is super dangerous. If we desolder the storage device, there's a high chance that we tamper with the information. And even if we are trying to get it working on another ABAC ECU, there's also again the danger that we tamper with this information. But Pete and his team don't see any other option here in analyzing the ABAC ECU any further. So what he's doing right now is he is desoldering the flash component. Here we can see a screenshot how something like this looks, and gets another ABAC control unit from a Tesla. Those aren't that expensive, and you can get it from, for example, eBay, and installs it again onto the device on the new ABAC ECU, which is not damaged. So after this pretty complex and pretty long process, he finally can collect the information using Tesla's own EDR tool. This is pretty straightforward. You just need to power it on with a corresponding interface, plug it into your computer here in USB-C cable, and then collect the information using the official Tesla's EDR tool. After you collected this information, you receive a JSON file. JSON file introduces some metadata, but also some hexadecimal blobs introducing the actual information. For us as investigators, again, data interpretation, we cannot interpret those hexadecimal blobs, just some big blobs with a lot of numbers. Again, here we rely on Tesla to interpret the information. And this is where Tesla's own EVR reporting service comes into place. On their website, we can upload an EVR file or a JSON file, which contains the relevant information. And we get a good-looking, fine-looking PDF report back with all this information, what happened or what got recorded by the airbag control unit. So what Pete does here is just upload the file, hit submit, but we get an internal error here. And Pete states one main question here, well, he did everything right. Or, so what is actually the issue here? So let's think back. So we extracted the flash chip from the damaged device. We installed it on a new component. Then we collected the information using Tesla's EVR tool from the new component, which holds the data from the old device. So if something would have happened or something got wrong with desoldering and resoldering the device, we wouldn't even got any information, or we got an error from Tesla's EVR tool, right? So usually those components hold additional information. So if we have an airbag ECU, it holds some information about in which vehicle it's actually got installed in. And usually the vehicles are identified by a unique identifier called the vehicle identifying number, VIN. So obviously we have two different airbag control units or airbag ECUs from two different cars. So they introduce two different VINs, right? So what we need to do within the report, we need to identify where is the VIN located at. And usually, since Tesla isn't stupid, they also introduce a checksum, which is related to the VIN, but also to the report, to the corresponding information afterwards. This was pretty easy to spot because if we look at JSON files from an EVR report on the internet, we can see that they introduce a checksum. And we also can see such a checksum in the actual .json file. So what we need to do right here is we, basically modify the JSON file, but only the VIN and only the checksum without changing the data, re-upload it and hope for the best, so to get a PDF file. So far so good, but if we think back, we forgot something at the beginning, right? Within the digital forensic in fundamentals, I showed you the 6 Ws. So we just straight up jumped into analyzing stuff. But we could analyze stuff forever, right? So we need actual questions we want to answer. If we think back, the police officer just gave us the airbag ECU and told us, well, do some magic, right? So we actually need some answers or some questions which we want to answer. And then if we can answer them, we can actually report them to the stakeholder itself. So in this case, Pete just calls the police officer again and asks him, dude, what is actually your questions in the investigation? Because it also depends highly on how we proceed in the investigation itself further. So if you're able to, for example, damage the device itself even further. And the police officer comes back with a few questions. So first one is, can you reconstruct events? This somewhat states that the police already tried to collect this information using the standard Tesla EVR tool. And we saw it before that this wasn't even possible for us. So we had to desolder the flash storage systems. Second question is, can you get the report from Tesla? This is what we are trying right now, or we tried. And third one, is pretty specific. Did the vehicle accelerate by itself? So if you think back, the driver told that during the automatic parking, the vehicle accelerated by itself. So the police tries to answer this question. And luckily, after we changed the VIN and the corresponding checksum, we got the report. So we got the PDF report. Awesome. Next up, we can focus on question 1. So, well, just try to reconstruct the events which occurred. So here we can see a screenshot of one of the tables which is included in such a PDF file. To explain how you usually read this information, we can on the left-hand side, sorry, we can see a time column. The time column introduces different timestamps from -5 seconds to 0 seconds. -5 seconds states that all this relevant information in this row is 5 seconds before the accident happened, so before the final event occurred. And 0 would actually state the point in time where the event occurred. So if we look at the table right here, we can see different information. So the time I just explained, also something called service brake, which is all off, something called stability control, which is not engaged, and something called ABS activity, which is off. So ABS activity is the ABS, so automatic braking system. This is off. So, okay, this is something we would expect in a crash with high accelerations and high speeds. Stability control, I guess, is something related to the stability of the vehicle, not engaged. Okay. But what actually is the service brake, which states here that it is off? Luckily, in those reports, we have some documentation on what those different terms are actually standing for. So if we look through the definition for the service brake, we can spot something interesting. So the service brake gets a flag on if the pedal is being applied by the driver, and it gets the flag off if it's not applied by the driver. If we look at the table of our report in this case, we can see that it is off. This is weird, right? Because this would state that the brake was not pressed. And if you think for yourself that, let's imagine you're automatically parking, or the vehicle you're sitting in is automatically parking into a parking lot, and then suddenly it's accelerating like crazy. You obviously try to press the brake as fast as possible. But this information we can see right here states the opposite. So what we do right now, or what Pete does right now, is document it. So document brake was not pressed based on the information we collected. So let's look at the next table we can find in this PDF report from Tesla's EVR tool. Again, here we have the time column, a vehicle speed column, an accelerator pedal column, and a rear motor speed RPM column. So if you look at it even in a detailed way, we can identify some weird but also interesting behavior. So first of all, look at the vehicle speed column. We can see here that 5 seconds before the event, vehicle speed was approximately 17 kilometers per hour. Then approximately at 2 seconds, we are at 14 kilometers per hour, and then suddenly the vehicle gets faster, so the vehicle speed increases. So from 14, well, a bit down to 13, and then again 14, 18, 22, even 26 kilometers per hour, which is pretty fast in our parking situation. Let's correlate this with the accelerator pedal on one column to the right. Here again, we can see that at approximately 4 seconds, the percent, so how hard is the accelerator pedal pressed, is increasing up to the point where the crash happened. So 14, 15, 16, 17, 18, 20, even more. So at approximately 0.5 seconds before the crash, the accelerator pedal was pressed for 100%. So hit it like crazy. So one major question here is also, why is this not directly linked to each other? So in the time column, time row, well, if you're driving a car, or imagine you're driving a car, if you hit the accelerator pedal, it obviously, even if it's an electrical vehicle, is not accelerating directly. So it's taking some time due to physical constraints. But if we interpret this information here, we can state that the vehicle speed was increasing, but also the accelerator pedal was pressed harder and harder up to the time where the crash actually happened. So let's look at our documentation. Well, we can see in one table that the brake was not pressed. In the second table, we can see that the vehicle speed was increasing all the time. So up to the point where the crash happened. And also the accelerator pedal was pressed harder and harder. So what could have happened here? If you think about, just imagine if you would be in this situation, you're automatically parking or sitting in a vehicle which is automatically parking. And then suddenly the vehicle is accelerating by itself. What you would expect from your personal experience is that you try to brake as soon as possible and as hard as possible. But we can see right here the complete different. So what we see for information from the accelerator pedal and the vehicle speed, this is something we would expect when in a complete opposite. So we would expect something that the brake was pressed even harder and harder because we want to stop the vehicle. We want to prevent something to break, to cause an accident. So one interpretation we could state here, which is not our case as a forensic investigator, because we only need to present the information and the interpretation of the information. So what actually could have happened is up to the police. But what we could see right here is maybe the brake and the accelerator pedal was mistaken by the driver. But there's still one question missing, which is, did the vehicle accelerate by itself? Based on this information we collected from the airbag control unit, we can somehow answer it, but not really that relevant, because not really that specific, because we are lacking information from in-vehicle systems. There's no information or indicator in this report we consumed or collected about the case itself. So was the autopilot, for example, enabled? For this information, or for this to answer this question, we need information from the autopilot. Sadly, we are not allowed to get access to the autopilot logs in this case, or Pete is not even able to collect this information. So what we can clearly see in a summary right here is we are able to answer two questions. Can you reconstruct the events? Yes, we did. And can you get the report? Yes, we did it also. But the third question, did the vehicle accelerate by itself, isn't that easy for us to answer, because we are missing some information from, for example, the autopilot. But there are a lot of more open questions in this case. First one is, we collected this information using a proprietary tool from the manufacturer. is this EVR data even trustworthy? How is the integrity of this information? Is its integrity protected? Usually for airbag control units, that's not the case. So something could be changed, could be tampered with. We sadly didn't have access to evidence we really needed to answer the questions the police officer stated to Pete and to us. So we need access usually to the vehicle itself to collect more information. Because in the fundamentals part of this presentation or of this tutorial, we saw that vehicles are complex systems. So we usually have a lot of data storage systems which we could collect information from. And this information is pretty interesting for us in cases where we need to correlate information or data. So here if we would have different data sources, for example, from the control, from the ecosystem or the engine monitoring systems, or even the autopilot, we could correlate all these events. So is there more information about the brake being used? Is there more information about the autopilot being on or off? So this is where correlation comes into place, which wasn't able in this case, because we only have airbag control unit information. And we also have no validation of the data sources. It's kind of similar to the first open question about trustworthiness. We aren't able to validate information which we collected because there aren't any hashes of something that's changed in the course of time. There are no checksums which we can validate. There are no signatures. And if we only have one data source, this is pretty hard to argue, that the information we collected is actually the correct information, what happened in the past. So what we need in automotive digital forensics is we need more generalized approaches. Right now, we have the issue that if you have an investigation, you're mainly focusing on one specific component, collect information and try to interpret the result and build evidence trails. But the approaches aren't generalized enough because we are lacking very hard on correlation, because correlation is key if we don't have any integrity information on the data we are collecting from modern vehicles. If we aren't able to prove that the data we are collecting is actually the right data due to its integrity or authenticity, we need to correlate it from different sources, from different entities, in order to prove that this information is somewhat true. We also have seen in this case that we are only able to interpret the information using a proprietary tool and the help of Tesla. So we need to normalize the data itself. If we are able to normalize it, correlation afterwards get easier too. And we need new and better tools. This is pretty interesting because we shouldn't really rely on one specific tool to interpret one data asset. If we use different tools, we can correlate them, or not even correlate, we can compare them if some tools maybe causes some errors or interpretation issues. And we need to view on the vehicle, but also on the vehicle ecosystem as a whole. So not only, again, on one specific component, the airbag control unit, look at the ecosystem. What information, for example, was collected from the passenger's phone, if he had a phone? What information was streamed to Tesla's backend? Was the ecosystem enabled? What information did we got from the ecosystem? All this information would be really interesting here in this case. So this is a long time road for us, or a long time ahead for automotive digital forensic investigations to get better. Right now, we are at the beginning in this domain. So what we need here are new proposals, new tools, new approaches. And this is what I'm trying to achieve with my research work. Thank you very much for your attention. And I would be happy to answer some questions from you.
Thank you very much, Kevin, for your presentation. We have any questions? No?
Yeah, I have a question.
Of course, Petre.
Petre, how are you? Good or
Hi.
very good? Everybody, it's feeling good. Thank you, Kevin, for accommodating a little bit the late schedule. Actually, you missed Asen, but again, I promise we will have Asen for you next year somewhere. Yes.
Awesome.
Question is, one particular question, not necessarily related to the process, which I understand it's kind of very well heuristically standardized, but this is also kind of art. It's not only a science, it's a feeling. You need some knowledge embedded in your mind how to approach different systems, because there is multiple prongs, and you just listed a few possible cases. Of course, you had a little bit more than that. So question is, in your experience, what is the real status of application? How people are reacting? Are they just guessing or just following a quite well-defined track where you can backtrack and learn why we failed somewhere?
Thank you very much. Very, very good question. So in digital forensics in general, not even automotive digital forensics, the investigation results highly depend on the experience of the investigator. So here is where we need, this is what I stated at the end, new approaches or generalized approaches, how to actually interact with evidence items, which in our case are cars or the ecosystem. So it's a very broad research topic which we need to address in order to get a generalized opinion on how to approach the vehicles itself, to get as much information as possible from those. And we also need good documentation on the manufacturer and component side, what data is actually stored in our modern vehicles. This is a big issue or big questions we can't answer right now. Okay,
so let's summarize for myself now. 20 years ago, the big problem we had in testing and in software development was the poor quality of documentation.
Yeah.
And now you say, yes, we still have a poor quality documentation for diagnosing and digital forensic as well. Is this correct?
This is correct, yeah. But it's not only that this information is lacking. Sometimes there is good documentation, but the documentation is not available to the investigator itself, because sometimes vehicle systems are extremely complex. A lot of the stuff is not shared by the manufacturer due to intellectual property issues. So sometimes we have to come up with some tricks to actually interpret the information itself, yeah. So it's not only that the documentation is not there, sometimes it is there, but not available to the investigator itself.
I see. Do you see a reluctance of experts in taking time for writing a good documentation? And I'm telling you why, the background of the question. It's usually in software development and in LexPay, where there are a lot of experts, they consider as a second level citizen as writing documentation of what they are doing. Not necessarily of not sharing the knowledge, but considering that it's a minor activity, is not on your business, on their business. Is this the same feeling on your side?
Yeah, I would say that's the same feeling, because the people that introduce new components and the corresponding technologies, which usually introduce software, well, they are common developers, but in the automotive domain. So this is a lot of stuff I see here is that we have some interesting technologies which are pretty smart, but the documentation itself is lacking. Definitely, it's pretty similar to common IT if we compare both domains.
I see. When forensic specifically, it was question of having a kind of a repertoire of directory of all possible cases, and then not necessarily from that, from the cyber protection. And the opponent said, if we have a standard of how to approach different things, this is a salt and a bread to the hackers. Because if you have a well-documented case on something bad that might happen and how you repair or fix it, then it will be very easy for somebody to tweak a little bit this one. Is this the same story on your side? Do you feel this?
I would answer yes and no.
Correct.
So it depends. Or first, if you have a general process how you approach a vehicle in a forensic investigation, if it is extremely detailed, you automatically lose the creativity of the investigator. But if you, for example, state a pretty broad approach how to investigate information from a vehicle, so for example, where are interesting components you want to look at? How do you collect this information? This information can be pretty easily shared with attackers because, well, the attackers are just know that there is some, the people look into these components, but obviously he has to, or she has to actually attack those components to achieve his result. So this shouldn't be an issue in my opinion. If it isn't that detailed, but I'm not a fan of detailed approaches because, as I stated, you lose the creativity of the investigator.
I see. Very well point.